let me just start the second talk with a slight correction to yesterday. We have seen this main theorem about the representation theory of quivers and the classification problem for representations. We had this trichotomy between having just a discrete classification, discrete plus harmlessly many continuous parameters, and out in the wild where the number of continuous parameters growing quadratically. Let me assume, please make this correction, that the quiver is connected. And then these if and only ifs, which I wrote down yesterday, are really fine. So if your quiver is connected, then the problem of classifying isomorphism classes of representations is a discrete problem, if and only if the underlying unoriented graph is just a Dynkin type ADE quiver. And then you can omit this disjoint union because of connectedness. You have discrete plus continuous parameters growing linearly, if and only if Q is an extended Dynkin quiver, and the number of continuous parameters grows quadratically. And now I forgot to put on my mask so that you can see me. If and only in all other cases. The problem yesterday was, just to give you a counterexample to what I stated yesterday, if you have some situation like a quiver having both a component of extended Dynkin type, A2 tilde, and a component of Dynkin type. That falls into the second category, but not in the formulation which I gave yesterday. So to be on the safe side, let me just assume this the quiver to be connected, and then everything is fine. Okay, so that was a slight connection. Let me just briefly review what I did yesterday. What was the logic? And after that, we will start with the new topics. So the logic yesterday was we looked at classification problems of linear algebra and observed some kind of trichotomy between the hardness of the classification problem. Then, using the notion of quiver representations, we were able to translate this into an algebraic categorical setup and in a geometric setup. And the algebraic setup is classify isomorphism classes in a category of representations, a nice abelian finite length C-linear category. So that was the algebraic approach. And we also had a geometric approach, classify the orbits of a group GD in a vector space RD encoding all the representations. So that was the geometric approach. And as I said yesterday, the great thing is that we can somehow combine these approaches or play them against each other, and this we'll do continuously. But from this geometric formulation of the classification problem, we got the idea how to define moduli spaces, how to define geometric objects encoding the continuous parameters. Namely, the idea is to form something like an orbit space. Form something like this, something like an orbit space. But the question is how to do this. So that was the logic yesterday in attacking such hard linear algebra problems. And now we will do this today and make a first attempt of constructing such orbit spaces. And we will do this using invariant theory. And I just need a tool to erase the blackboard. Okay, so let me clean the blackboard professionally. Which increases visibility anyway. So this will now be the first part about construction of moduli spaces. And we'll make a first attempt, which almost fails. and then we'll make a second attempt, which is better. So, but this is now part 3 of the talk, construction of Quiver moduli spaces. And now we make a first attempt, which is very classical. And it almost fails, except for, well, you will see when it works. And our first attempt is just to think about this question in some situation where we have an algebraic group acting on a vector space, how to form quotients. Thanks a lot. So let me first explain this classical story of invariant theory. So given a linear action of an algebraic group, G, on a complex vector space, V, how to form a quotient, how to form an orbit space. Well, the naive idea is to do this set theoretically, just take the set of all orbits, or you could do it point set topologically by just saying, well, it inherits the quotient topology from V, but that usually is an extremely bad topology. So we have to do something better. And the key to make the correct definition of what a quotient should be comes from a categorical intuition. Namely, let us try to reformulate this idea of set theoretically, taking the set of all orbits. Let us formulate this with the aid of a universal property. So let's define quotient of V by G is a set space, let's say an algebraic variety. It's an algebraic variety X together with a G invariant quotient map pi from V to X, which fulfills a universal property, namely it is universal for G invariant maps, which is universal for G invariant maps. And what does this mean, being universal? Well, you have V, you have this map pi, which is part of the datum of a quotient. And then for any map F, for all F which are G invariant, you ask for a unique factorization F bar. Oh, sorry. Is it better now? Thanks. Okay, so let me repeat it. For every G invariant map F, you ask for existence of a factorization over X such that this diagram commutes. Well, this is a classical formulation of some universal property. And if you think about it for a minute, if you do this not with varieties, but just set theoretically, if you just have an action of a group on a set, and you ask for existence of a set which is universal for invariant maps, then you will see immediately this set is just the usual space of orbits, set of all orbits. Yeah? So set theoretically, the standard orbit space would fulfill this universal property. But now we are doing this in the category of algebraic varieties. And more precisely, this is the definition of a categorical quotient. And it's not so clear whether such an object really exists. But the great thing is, under very reasonable assumptions, it does. And we can say almost explicitly what it is. So now let me formulate a theorem which one should attribute to Hilbert. Not in the precise formulation which I give. So we should add Mumford. So theorem Hilbert-Mumford. You need to assume one structural property about your group. It should be a reductive group. If G is reductive, linearly reductive, which we don't have to define, but I will just tell you that the group GLN, or products of GLN, SLN, orthogonal groups, symplectic groups, finite groups, products of all of them, they have this property. Yeah? So many of the standard groups which you encounter in such group actions have this property of being reductive. Some others don't. So for example, if you have a Borel, a group of upper triangular matrices acting on something, that is not reductive. And then this theorem doesn't hold. But still, I mean, it holds in a vast generality. So it's really, really difficult to write down counterexamples to what I tell you now. If G is linearly reductive, such a categorical quotient exists. And because it is defined by such a universal property, then of course it's automatically unique up to isomorphism. Yeah? It exists, and we can say precisely what it is. We can just define X as follows. Take the coordinate ring of the vector space V. So just polynomial functions on V. And take all the polynomial functions on V, take the invariant, G invariant polynomial functions. Now the great thing is, this is a finitely generated algebra again, so it qualifies as the coordinate ring as of an affine variety, so we can take its spec. So, and let me remark, this is the ring of G invariant polynomial functions on our vector space V. So you can do this very concretely. You could do the following. So how do we actually write down the quotient? Well, you could just take generators of this ring of invariants. So if F1 and Fn are generators of the ring of G invariant polynomial functions, you could just look at the map from the vector space to affine n space given in coordinates by F1 to Fn. Let me call this map F. And so the image of this map does the trick. This is how you could do it concretely. Well, the problem is, of course, to find generators for the invariant ring, but we will see situations where this is actually possible. Take generators of the ring of invariants, put them together to map to affine space. It has some image, which in general is difficult to describe, but this image is automatically the quotient. So, okay, then we have a quotient. We cannot expect this quotient to be an orbit space like set theoretically. It does not parametrize all orbits. But what it does is X parametrizes the closed G orbits. In your vector space V. The closed orbits. Well, this is actually quite reasonable because, well, there might be closed orbits and non-closed orbits. So this is a closed orbit, this is a non-closed orbit having this closed orbit in its closure. And polynomial functions are not able to distinguish between these two orbits. Yeah? because one is in the closure of the other. Polynomial functions just can't do this. So it's quite natural to expect that we cannot parametrize all the orbits, but all the orbits which we potentially can, the closed orbits, these are actually fine. X parameterizes the closed orbits. Aha. So that's what our quotients do. And there's, in fact, much more to say about this, but that's the short version of this classical result of Hilbert and Mumford. So now we are almost there. Now we can do this in the Quiver setup. We have our group actions of the group GD on the space RD, and let's apply this theorem and see what we get. And in fact, a lot is known about this, about what this construction gives, which I will tell you now again in one theorem. Let me clean the blackboard first. So, okay, so now as the group G, we take this group GD, the base change group. And as our vector space V, we take the representation space RD of Q. And just to make sure that you recall from yesterday, let me very briefly write down what the group and the space looked like as a reminder. So reminder from yesterday, we have the group action of GD on RD, and RD was the direct sum over spaces of linear maps along the arrows of the quiver, and the group is just a product of base change groups, one base change group for any vertex of the quiver. And the action was given more or less by something like conjugation, so symbolically. Yeah, that was the situation yesterday. Okay, and that's where we apply this theorem of Hilbert and Mumford to the geometric quiver setup. And it gives us the following theorem, which is attributed to Lebrun and Procesi. And okay, I think all parts are just Lebrun and Procesi. Okay. In the 1980s. So, first part is such a quotient exists. Okay, this existence we already know from Hilbert Mumford, because Hilbert Mumford said this quotient exists if the group is reductive and we have a linear action. This is fulfilled here. Conjugation action is linear and the group is the product of GL, so it's reductive. So this quotient exists. The second part of Hilbert's theorem says it parametrizes the closed orbits. So what are the closed orbits for this action in the quiver situation? Please recall the orbits for this action correspond canonically to the isomorphism classes of quiver representations. So being closed for the orbit should be reflected in a representation theoretic property of the isomorphism class. And indeed it is. The orbit of a representation is closed if and only if the representation is semi-simple. It parametrizes isomorphism classes of semi-simple, so direct sums of simples or direct sums of reducibles, so completely reducible, semi-simple representations of Q of this given dimension vector. D. Aha. Okay, so now we know a good name for this space. And this name I will continue to use. So we call this M, like moduli space. for representations of the quiver of dimension d, and it parametrizes the semi-simple, so let me call it MDQ semi-simple. We will see other moduli spaces in the next section, but this is the first part. Okay, that's the first part of this theorem. What can we say about this space? So here are some basic geometric properties. So this space is affine. Well, because the quotients we construct are always affine varieties. They're a spec of a ring of invariants. Irreducible. Well, they arise as quotient of some vector space, which is irreducible. They may have singularities, quite severe singularities, but at least it is normal. Because the quotient of a vector space by linear action is always normal. It's affine, irreducible, normal, and there is some kind of expected dimension, which is not always the right dimension, but there are enough interesting cases where it is, of dimension 1 minus sum over all vertices, di squared, plus sum over all the arrows, di dj, if a certain condition is fulfilled, which is non-trivial. And let me write it down. It is of this expected dimension if for this particular dimension vector there exist simple representations. So now if you are only used to quivers without oriented cycles, then this might sound strange to you, but I will explain what happens in a few minutes. So this expected dimension is reached. If there exists a simple representation of Q of this dimension vector D. And yes, last part of the theorem, and then we can have a short break and you can ask questions. Third part is we can even make this moduli space explicit. We can explicitly embed it into some affine space because in principle, generators for the ring of invariants are known. In Hilbert's theorem, I wrote down how you can get this moduli space as the image of a map to affine space if you know generators for the ring of invariants, and generators for the ring of invariants are known, at least in principle, here. The generators are, well, you have to take enough of the following infinite series. The ring of invariant functions C RDQ GD is generated by traces along oriented cycles. So that's the first theorem. These are our first moduli spaces, and now let's have a break for questions, and then I will show you some examples and discuss this result and its relevance. Okay, that was the first half.
Okay, thank you. So feel free to ask questions during the short break.
Yeah.
In the second statement of the theorem, this if, is this an if and only if, or just if?
That is, oh, that's actually an if and only if, yes. If you have no simple representation at all, then the generic stabilizer is definitely bigger than just the scalars. Yeah, it's an if and only if. Thank you very much.
Okay, thanks.
So it's it's already clear that there's something strange about this theorem, because I mean, most of the quivers which we have seen yesterday in these motivating examples were quivers without oriented cycles. And here now I'm just talking about quivers, about traces along oriented cycles. So something's wrong here. That's clear. I will clarify this point. And that's the reason why we somehow have to change our strategy anyway. But well, we'll come to this.
So there is one question in chat. I will read it aloud.
Yes,
And
please.
the question asks, can you say a bit more on the case when there are no simple representations?
Yes, I can say something about, well, I could write down a formula for the dimension, maybe.
That is precisely the follow-up question. Is
yeah, okay. Yes, I mean, yes, in principle, yes. Oh yeah, okay. Yes, when I come to the examples, I have at least one example where we are in this case where we have no simples, and then we can see what happens. And from this example, we could then develop a dimension formula without this assumption. Yes.
okay, great. I will ask the asker of his question to wait.
I also would like to mention there is a numerical criterion for this existence of simple representations of a certain dimension vector, also due to Lebrun and Procesi. It's a bit technical. Yeah. It's a bit technical to formulate, so I try to avoid it, but like this is somehow efficiently decidable. Yeah. Purely numerically from the shape of the quiver and the dimension vector, whether you have simples or not.
And there's another question in chat.
Yes.
Are orbits of semi-simples closed?
Orbits of semi-simples are closed. Yes. Okay. Let me just make two additions to what I wrote. So let me first note what I said. This is numerically decidable. And let me also make a remark on this. So this is really what happens here. In general, this quotient parametrizes closed orbits. Now here I wrote it parametrizes isomorphism classes of semi-simples. And what is behind that is really the statement, the orbit of a representation, let me just write it like this. So V is this, in fact, this whole tuple of linear maps. This orbit is closed if and only if V is a semi-simple representation. Yes. I can also give you very briefly the idea behind this. I mean, a full proof is also not too difficult, but let me just show you the idea. Think about the conjugation action for one matrix. If you understand that in this case, then you have the general case. So the closed orbits for the, let me write this as an example. Maybe that's a good idea. Example, let's just consider the conjugation action of GLD on square matrices. Wire conjugation. So I claim that the orbit of a matrix is closed if and only if the matrix A is diagonalizable. And let me just show you one direction. If the matrix is not diagonalizable, what do you have? Well, then it might involve a Jordan block. That would be a 2x2 Jordan block. Actually, it's not necessarily in the Jordan normal form to write down a 1 here. It could be any t which is non-zero. Yeah? So let's look at this whole family. It's an affine line. So for t, a free parameter, that's an affine line in this space here. And well, for t non-zero, it belongs to the orbit of the standard Jordan block. You can find a base change transforming this t back to 1. But for t equals 0, it belongs to the orbit of the diagonal matrix, lambda 0, 0, lambda. Yeah? And so pictorially, so here you have this affine line, and you have the single point. Almost everything in this affine line belongs to one orbit, but this special point belongs to another orbit. And so you can see that this orbit belongs to the closure of that orbit. So the original orbit wasn't closed. Yeah? And with some more effort, you can really prove that this is if and only if. So that is some of the typical example. And that's basically, if you know this proof, then you can generalize it to Quiver representations.
And there's one final question. Is there a sufficient criterion to ensure smoothness of the quotient?
Haha. Yes, there is. Let me postpone this a little bit to the point where we have these more fancy quotients, moduli spaces of stable representations, and that's the point where I wanted to discuss smoothness and the relevance of smoothness anyway. Yeah.
Okay.
So if it's fine, then let's postpone this. I will deal with this anyway.
Okay. Thank you very much, and then we can continue the lecture now.
Wonderful. Okay. So yeah, I really like this idea of having this short break, and I will always try to somehow decorate what I wrote by somehow comments to the questions. I really like this. Okay, so let me first discuss this point here. So if you know about quiver representations for acyclic quivers, then you know the simple representations of a quiver. That's usually extremely simple. You just have one simple representation for each vertex, namely one-dimensional simples. So you might wonder, what's going on here? Simple representations of dimension vector D. You also wonder about traces along oriented cycles. Well, the problem is this theorem is empty if your quiver has no oriented cycles. That's a pity. And that's why we failed with our first approach to forming quotients. And we have to find a better approach, definitely. Yeah. So let me just remark. So the theorem is empty, or say trivial, if Q is acyclic. So it has no oriented cycles. Why? Well, because if you have an acyclic quiver, then the only simples are one-dimensional, and for each dimension vector, you have precisely one semi-simple representation. Well, if you have only one semi-simple representation, then your moduli space, your quotients, is just a single point. Well, it's okay, but not too interesting. Yeah. So the theorem is empty or trivial if Q is acyclic, since then there exists a unique semi-simple for each dimension vector D. Namely, let me write down this representation. Well, a quiver representation consists of vector spaces, and as arrows, we just take the zero map everywhere. That's it. That's the only semi-simple. Yeah? And then your theorem is obviously trivial. So this theorem is only interesting if Q has cycles, and typically lots and lots of oriented cycles. Yeah? But then it really tells us something about these quotients. And if you say, well, but now I'm really interested in acyclic quivers, well, our construction of quotients just wasn't the right thing to do. And we will analyze this problem in the next section. But let me first stay here and now assume for the next 20 minutes or so that our quiver has typically lots of oriented cycles. And let's do some examples. And I will write down 3 or 4 examples and then really write down what these quotients are. So to end this remark, theorem is empty if Q is acyclic. So the moral is we need a better quotient. Desperately. Let's come to this in the next section. But in general, let me do some examples. So let's first do the example of a single loop, i.e. adjoint action of GLD matrices on D by D matrices. Then the quotient is known classically. So one way to write down the quotient map is the following. So we map to affine D space. Namely, we map a matrix A to the coefficients of its characteristic polynomial. The coefficients of the characteristic polynomial. Well, the characteristic polynomial of a matrix is invariant under conjugation. Yeah? And so it's invariant. The whole polynomial is invariant. In particular, the coefficients are invariant. And now these invariants already separate all the closed orbits. The closed orbits, as I told you, correspond to the diagonalizable matrices. To separate the different diagonalizable matrices, you have to be able to separate the possibility of eigenvalues. Well, but all the eigenvalues are encoded in this polynomial. So that was a very quick and informal proof that this is a quotient. Yeah? So that's the quotient. And here you already have the situation that this quotient has not the expected dimension. Because, well, the expected dimension of the quotient from this theorem would be 1 minus d squared plus d squared. Right? Because you have one vertex and you have precisely one arrow. Well, this is obviously not one-dimensional. So here we see the situation that there are no simples except in dimension 1. For d greater or equal to, generically, A is conjugate to a diagonal matrix. So it is a direct sum of d one-dimensional representations, because direct sum always means just this block matrix form. Yeah. So this is a situation where, in general, you don't have a simple. We'll see in a few minutes that if you have two matrices under simultaneous conjugacy, so the two loop quiver, this changes dramatically. In any dimension, almost everything is simple. Okay, so now I can also answer this question of how to solve this problem here. Well, in computing this dimension, let me do this in blue because blue is the color for answering the questions. So how do you compute the dimension of the moduli space of semi-simples? Well, you take the dimension of the space minus the dimension of the group, but then you have subtracted too much and you should add the dimension of the generic stabilizer plus dimension of the generic stabilizer. So, for example, what is the generic stabilizer here? Well, the stabilizer of a diagonal matrix is just a torus. So it's d-dimensional. Yeah. So in this situation, we would get the calculation d squared minus d squared plus d, which equals d, which is indeed this quotient. Yeah? So all you have to do is, for a given dimension vector, calculate the generic semi-simple type of the representation. If you know the semi-simple type, then you can calculate the generic stabilizer, and this formula tells you the actual dimension of the moduli space. Yeah? Okay, and this also proves part of the theorem, because if your generic representation is simple, well, the stabilizer of a simple representation by Schur's lemma reduces to the scalars, so you get this minus this plus 1, and we are done. So that's the proof for this dimension formula. So that was the first example. That's just the classical adjoint action, so maybe we can do something more interesting. As a second example, let's look at a quiver with two vertices and lots of arrows in both directions. But let's keep the dimension vector very small, namely let's keep it 1, 1. but just to understand how we can somehow produce invariants. All right. So, second example, just check. Yes. Okay, so let's consider the quiver having two vertices, m arrows in one direction, n arrows in the other direction. And let's consider the dimension vector 1, 1. We could do a bit better. We could do 1k. But because I want to recycle this example later, let me keep it simple. And so I claim the moduli space of semi-simples in this situation is a cone over the Segre embedding. The cone over the Segre embedding from Pm-1 cross Pn-1 into Pm times m-1. Maybe I did these shifts a bit wrong, but let's see. So the cone over the Segre embedding, which realizes products of projective spaces as a projective variety. How do we do this? Okay, so what is the representation of this quiver? Well, the vector space is one-dimensional, so dd. The arrows here in this direction are represented by numbers a1 to am. These are represented by scalars b1 to bn. And our theorem, the part which I erased, says we can find all invariants by taking traces along oriented cycles. Well, let's do this. Okay, so what are oriented cycles? Well, we could start at the left point, go AI, and then go bj. That's the 1-by-1 matrix. The trace is just AI bj. Yeah. So let's take the following. We map this to a huge affine space with m times n coordinates, mapping this representation to the collection of all a, I, bj. I from 1 to m, j from 1 to n. Okay. You could form an m by n matrix out of all of these, and it's an m by n matrix which is precisely of rank less than or equal 1. Yeah. Or you could just look up what is the Segre embedding. If you put A coordinates here and B coordinates here, then you see the image of the Segre embedding is precisely the tuples which are of this form. Yeah. Okay, so these are some of the invariants. We don't need more because you can easily see that now all the closed orbits are separated. Okay, so that's the second example. Third example, which I will leave as an exercise, a classical exercise. Let's look at the quiver now out into the wild, the famous pairs of matrices, square matrices under simultaneous conjugation. And let's keep things simple and look for dimension vector 2. So pairs of 2-by-2 matrices under simultaneous conjugation. So I claim that the moduli space is isomorphic to an affine 5 space. And the 5 coordinates which you need with coordinates, so the coordinates are these generators of the invariant ring, and you need 5 of them, trace of A, trace of A squared, trace of B, trace of B squared, trace of AB. So these 5 traces, so saying that this is an isomorphism is 2 claims. First is the claim, if you take these 5 traces, they can separate all the closed orbits. So there are enough of them. And that the moduli space is the whole of A5 means any configuration of these 5 invariants can be reached. So you can write down pairs of matrices having prescribed trace A squared, trace B squared, trace AB. Okay. Everything else is difficult, but yeah. let me elaborate a bit on this case of two loops and D arbitrary. And let me call this moduli space just for a minute, just XD. XD. It's the moduli space for this situation. So what do we know about it in general? Just to illustrate this, this dimension formula. Well, the dimension, so it's affine, irreducible, normal of dimension. Well, 1 minus dimension of the total space of configurations. And the total space of configurations is pairs of D by D matrices plus dimension of the, sorry, 1 plus minus dimension of the group, which is D squared. So the dimension is D squared plus 1. So this is the expected dimension, yeah, by this general formula. Let's see that this is the actual dimension. So let's prove by hand that you have simples in any dimension. And this is a very simple linear algebra exercise if you see the trick. But once you are given the trick, it's easy to check. So it really suffices to write down one particular simple representation. The reason why it suffices to exhibit one simple representation is that the notion of being simple is open. So if you have one simple representation, then you have a whole open set of simple representations, and it's open in a vector space, so it's automatically dense. So simplicity is an open property. All right. So this is the expected dimension. So let me continue by saying this is the actual dimension. Because the following holds. So let me write down one pair of matrices. The first matrix you make as generic as possible. And we already know generic means diagonalizable. But let's also assume that the eigenvalues are pairwise distinct. And the other matrix is a cyclic shift. You shift the first basis element to the second to the third, and so on. The D minus first to the last, and then the last to the first. Yeah, cyclic shift. And I claim that this defines a simple representation. Okay, let's do this exercise. So now first we have to translate from this notion of quiver representation back to the linear algebra problem.
Yes, you can continue now.
Okay, wonderful. Welcome back. And now we have a really improvised situation with just a mobile session, but let's see how long it works. I will just do this example and then one quick theorem, and then we'll see how much we can do. So I was looking at the two-loop quiver, our classical example of an unsolved linear algebra problem, now with an arbitrary dimension type D. And I temporarily call XD the variety, the moduli space of C simple representations, affine irreducible normal, and we're just in the middle of the dimension calculation. So the expected dimension is D squared plus 1, drawing quadratically. But to match this expected dimension with the actual dimension, we have to prove that there are simple representations for this dimension vector. So we have to translate the notion of simple representation of a dimension vector back to the linear algebra problem. And that's quite easy. So simple representation means there's no non-trivial subrepresentation. And subrepresentation means there is a subspace of our vector space which is invariant under all these operators. Yeah? So simple representation means no non-trivial invariant subspace. And now I wrote down a typical example. I claim that this is a simple representation. So it's of the form a generic semi-simple, so a generic diagonal matrix, pairwise distinct eigenvalues, and the matrix giving the cyclic rotation of all the basis vectors. So and I claim that there are no non-trivial invariant subspaces. So let's assume for a second that there is an invariant subspace. If it's an invariant subspace and it is stable under this generic diagonalizable matrix, it automatically has to be a subspace which is spanned by coordinate vectors, some collection of the coordinate vectors E1 to ED. Now take this collection of coordinate vectors, and everything has to be stable under cyclic shifts. So you take a collection of coordinate vectors and cyclically shift them around. And then you automatically get all the coordinate vectors in the subspace. So if your subspace is non-zero, it automatically is the whole vector space. That was maybe short, just redo this exercise. It's really just simply an algebra exercise, but this shows this is a simple representation. And if you have one simple representation, then almost any representation is simple, because simple is an open property, and it's open property in a vector space. So this is a dense set. You have a dense set of symbols. All right. So this confirms this dimension. Very nice. And now this is actually the point where I can give you one application of Quiver moduli, which I promised at the very beginning of the first talk. I said that there are some quite surprising applications of Quiver moduli because they calculate rather non-trivial things. So I'll now show you that these moduli spaces somehow compute for you a very non-trivial product factorization of Rogers-Ramanujan type. So to prepare this, let me just say that XD is exact for D equals 1 and D equals 2, a singular variety. Question? Oh.
No, I think someone was unmuted by accident. No, there's no, everything is fine. You can continue.
Wonderful. Okay, so XD is typically a singular variety, except in case D equals 2, where it is an A5, and in case D equals 1, where it is an A2. But it's typically singular. If we want to look at, say, topological invariants of this variety, well, it's a complex variety, so it's a complex space, and you could do topology in it, looking, for example, at cohomology. Well, to just look at cohomology, like you learned in algebraic topology, like singular cohomology, is quite a bad idea for singular varieties. There's a much more sophisticated cohomology theory for singular varieties, which is called intersection homology, which I will not define, but it exists. Yeah? That's what you usually want to know about cohomology theories, that they exist. We can consider its intersection homology IH of XD, and technical detail, because this is not a projective variety but an affine one, I want to consider compactly supported intersection homology. Compactly supported intersection homology. Well, I'm not really jumping away from an example to giving you one of the first, actually one quite non-trivial application of Quiver moduli. So this gives us homology groups, intersection homology groups, and we're just interested in their dimensions, in the Betti numbers. And these Betti numbers calculate something for us, which usually is extremely difficult to calculate, namely the so-called Euler product factorization. And I will just write it down because it can be done without any further notation in this case. And I will postpone all the details to, well, I guess the last talk next week on Thursday. So just to give you a cliffhanger, and you'll be interested in visiting next week. So let me clean the blackboard for that. I'll try to write large letters so that you can see it. So that's an outlook to something we will do next week, and it's a consequence of the so-called dt equals IC theorem, which I will discuss next week. The intersection homology groups calculate Rogers-Ramanujan type factorization. So the left-hand side is something which is usually called a Q hypergeometric function. So what I will write down is actually the function which is well defined somewhere in the complex numbers, but let's just take it as a formal power series. So let's take the sum over all d of q to the d squared times t to the d divided by 1 minus q times 1 minus q to the n. That looks a bit shocking and totally unmotivated if you see it for the first time. But, well, if you don't know the Rogers-Ramanujan identities, then look it up and you will see it's just this without the t term. Yeah? So this is a formal power series in two variables, q and t. And then what I would like to do is, I would like to write it as an infinite product, because that's what the Rogers-Ramanujan identities do if the t is omitted. So here's an infinite product. It also looks quite dangerous because it's a triple infinite product. Product over all d, greater equal 1, product over all integer I, product over all, say, k, which are non-negative, 1 minus q to the I plus k, t to the d, and now to the power minus 1 to the d, and now it's the dimension of the 2i plus d plus first intersection homology group of x. All right. So that's in several different ways. This is something which is okay. Thanks. So this is maybe something which is very unexpected in many ways. So first of all, this is the Q hypergeometric series. You have to like them to find them natural, and it's also debatable whether it's natural to write down such a product factorization. But just assuming that it is natural to factor such an infinite series into a product, it's quite unexpected that the dimension of certain homology groups for these moduli spaces of representations for the two loop group enter here, but they actually do. So this is one of the more surprising applications of Quiver moduli, and this result is actually quite deep because it relies on a quite deep theorem identifying certain Donaldson-Thomas invariants, which we'll see next week, to intersection homology of certain Quiver moduli. Yeah, but just to give you a little bit of an outlook of what will happen in the application part of Quiver moduli, these are some things to expect. Okay, now let me check the time. And, okay. So maybe because of the technical situation, I will just give a short outlook to the next lecture. Let's identify the problem with our quotient construction so far and see how we can do better. So now we come back to our logic. So we somehow succeeded with defining moduli spaces by making the notion of an orbit space precise in the sense of algebraic geometry. But we encountered the problem that at the moment we can only parameterize the closed orbit. And that at least for acyclic quivers, this is definitely not enough. Because for acyclic quivers, for any fixed dimension vector, we only have one closed orbit. So the moduli spaces of semi-simples for an acyclic quiver reduced to single points, which is definitely not what we want. So let me write down this problem again and then see what we can do to solve this problem. And the original idea for this is quite natural, but to actually formulate this, we have to make a choice, and this will then be an important topic for the next talk, next Monday. So, this is now part 4, construction of moduli spaces, part 2. And let me write down again what is the problem for acyclic quivers Q. We have only one closed orbit in the representation space, which means the moduli space at the moment is just a single point. So, how to parameterize more than the closed orbit? That's a big question. And the solution is the following. Let me just show you 2 group actions which we can really depict in the plane, and then study the potential solution from these examples, and I will work out the solution then on one. So examples. Let's look at the action of C star, just the multiplicative group of the complex numbers on C2, given by scaling both coordinates, tx on xy by tx ty. And let's also act with C star on C2 with weight 1 minus 1, so acting by tx in the first and by t inverse y in the second. So these are 2 actions of rank 1 torus on a 2-dimensional space, easy enough. And let's just draw the set of orbits. Now this drawing will of course be the drawing in the real plane, and you have to imagine the imaginary coordinates as usual, but the real picture substitutes to understand the principle. So I'll do this on a separate blackboard so that we have a large picture of these group actions. So that's C2. And what are the orbits for this dilation action? Well, you can delate the origin 0 as much as you want, it doesn't change. And this is one orbit. And all the other orbits are just pointed lines through the origin. And here, of course, the real picture is misleading because the orbits are actually, all orbits are connected, which you cannot see in the real picture. So these are the orbits. What are the orbits here? Well, the origin is one orbit, the pointed x-axis is another, the pointed y-axis is another, and all other orbits are hyperbolas. And again, the real picture is misleading because all these real hyperbolas are actually connected in the complex form. So here we see this phenomenon which we have encountered in the Quiver situation. And actually, that's a picture of RD for dimension vector 1, 1 for the Reineke Quiver with two parallel arrows. Yeah? That is, by the way, the picture for dimension vector 1, 1. If we have one arrow in pointing to the right and one arrow pointing to the left. So these are actual quivers. So the problem is here, this quiver is acyclic, there are no origin cycles, and indeed there is a unique closed orbit. And we're missing lots of different orbits. We're missing the whole family of pointed lines to the origin. So we're missing a whole P1 family. And so we have this orbit, and we have a P1 family of orbits. And of course, as quotient, we want to have P1, and not a single point corresponding to the closed orbit. So how can we do this? Well, that's quite easy. We just omit this bad point. Yeah? Just omit this bad point, take C2 minus the origin, and then you can take the quotient by C star, and this should be definitely a projective line P1. Aha, so this brings us to the first idea. To get more interesting orbits, we have to leave away all the bad orbits. We just have to make precise what makes an orbit bad. Yeah? And this problem is actually more difficult here. So what do you want to get here? Well, actually, all these hyperbolas are closed orbits, because a hyperbola is defined by the equation x times y equals some constant. Yeah? So all these hyperbola are closed orbits. There are two non-closed orbits, namely the pointed x and the pointed y-axis, and there is this bad closed orbit, the origin. So what would we do? We would again leave away the origin here. Just point the space and leave away the origin. But we still have a bad family here, because these two orbits, the pointed x and the pointed y-axis, cannot be separated by polynomial functions, because they both have the same point in their closure. Yeah? So here, in doing something similar to this example, leaving away the bad orbit, we have to make a choice. Either we declare the pointed x-axis as bad and the pointed y-axis as good, or the other way around. We have to make a choice. And that brings us to the notion of stability. So stability, manifold stability, is an ingenious device to make a choice, precisely a choice of a character for the group action. And after this, we have a notion of unstable orbits, and unstable orbits are precisely the bad orbits. Yeah? So this is the space of all. So that's informally the idea behind stability. The good orbits are those, and here we have to make a choice. So we have to choose the notion of good orbit. And these things will then motivate the definition of stability. Actually, manifold stability, not Fritzsche stability. Oh, this is much more simple. This motivates the notion of stability. You have to make a choice of what a stability notion is. And if you have a stability notion, then you can define a notion of good orbit, stable orbit. And the bad orbits are the unstable orbits. And then we will just leave away all these unstable orbits and try to parameterize the good orbits, the stable ones. And this will give us the modulized basis of stable Quiver representations. And this will be the first main result on next Monday. So, thank you very much.
Thank you very much, Markus, for this improvisation due to technical issues. There's one question about panning the camera, but I think it's better to move the board. Can you move the board with the pictures up a bit? The bottom board should be moved up a bit, I think. I think that was the request from chat.
So these are these very sketchy pictures, and
Yeah.
hopefully more pictures on Monday.
Okay, so we can have a question session now, or at least try to. So if people have questions, please unmute yourself, and Markus will ask your questions. So this part is still recorded, and will, after some heavy editing, appear on YouTube eventually.
I have a question. I'm Mirko. When you talk about the singularity of this moduli space, do we know anything about them? I know for Nakajima Quiver varieties, they are symplectic by work of Bellamy and Schedler. But in general, do we know anything about them?
Yes, we can actually almost classify them up to étale equivalence of singularity. Yes, I don't want to give the details out of the blue because I have to remember them, but I'm really happy to talk about this on Monday. I'll just make a note to myself that I should add something about the singularities. So there's a precise statement that all the singularities which appear up to equivalence look like the singularity of the origin, some of the worst singularity in some other quiver situation. Yeah, so very informally, the results will look like this. Okay, answers to questions always in blue. So very informally, you have something like you have this moduli space of CV symbols, and you have some singular point in it. So it's a singular point corresponding to some semi-simple representation. And then out of the semi-simple representation and out of the quiver, you build a new quiver, so-called local quiver, QV local, and some other dimension vector. And in this, you consider the origin. Well, in such a quotient of a vector space by a group, the worst singularity is always, if you have singularities at all, the worst singularity is always in the origin. That's the general principle. Yeah? And so you always have an étale equivalence of any singularity with a singularity in the origin for some other quiver situation. Yeah? And this is also due to Klein and Reineke. The paper from the late 80s, I think. You are basically using the Luna étale slice theorem to do this étale equivalence. But these singularities are really bad. Yeah? The singularity at the origin for the quotient of a vector space by a linear action is usually very bad. So don't expect anything nice like orbital singularities. It's a really bad singularity.
But do we know some property like rationality or those terms of minimal model property like KLT or something like that?
Rationality of the whole moduli space, you mean?
No, rationality of the singularity.
Ah. Rational singularities. I have to look it up, but I'm not just thinking about in the direction of theorems in invariant theory, the Hausdorff theorem and the Bochum theorem, saying that if you have a quotient of a vector space by linear action, then it is always Cohen-Macaulay rational singularities. This part is still recorded, so I'm asking this as a question. Please let me look it up. But I think we have rational singularities. But yeah, I will double check. Yeah, I mean, these are quotients, just invariant theory quotients for a linear group action on a vector space. So these are usually quite well behaved in their strong results. I mean, there's definitely Hausdorff telling us that the singularities are Cohen-Macaulay. I'm not totally sure about rational singularities at the moment.
There is confirmation in chat that by Boutot's theorem, it should
So,
be
right.
rational.
Okay. Thank you very much. Yeah, okay. So, yes, so all the singularities are, in fact, cohomology and rational. Yes.
Thank you.
So I suggest we stop the recording here and continue the discussion informally.
Thank you very much.